Hello. In this video, I'm going to explain problem 10 from the 2013 F equals MA contest. In this problem, we are asked to find which of the following options can distinguish a solid ball from a hollow sphere of the same radius and mass. So you look at the options, and one thing that you'll see is that actually three of them really are centered around gravity. And this may suggest that there is some clean way to rule them out, and indeed there is. So the thing is that you need to know a following fact, which is something that we sort of rely on all the time, but often don't consciously recognize, which is that if you have a uniform solid sphere or hollow sphere, you can treat, if you are outside the sphere, you can treat it as a point mass for gravitational purposes. So it exerts the exact same force, it produces the exact same gravitational fields and forces as it would if it were a point mass centered at that, centered at this, or located at the center of that sphere. So a classic example of this is, for example, if the sun were to spontaneously collapse into a black hole for whatever the reason, we would, presumably die just because the sun would not provide the energy we need for life. But it's not as though all the planets and asteroids and everything would just get sucked into the sun. And that's because the black hole sun would keep exerting the exact same gravitational force, since it would have the same mass, and it would just be a point mass at the center. And it's something that we kind of rely on all the time, because we often, when we do orbital mechanics, we often assume that the objects we're working with are point masses. And, if the objects are very far apart, this may be accurate regardless, but it's important for even objects that are relatively close to each other. So for example, like a satellite or a man-made satellite orbiting the Earth might be very close to the Earth's surface. And so the fact that we can still treat the Earth as a point mass for its gravitational calculations is very important. So this automatically rules out the three choices that I pointed to earlier. If we look back at them, you'll see that none of them really deal with anything inside the sphere, right? You can see orbit of a test mass around the object, so that doesn't go inside the sphere. You can see tidal forces applied by the object to a liquid body. Again, the liquid would not go inside the sphere, so there would be no difference there. And you can see measurements of the force applied to the object by a uniform gravitational field. And so that would be the forces of gravity acting on that object. Well, it has the same mass, and it would still have the same center of mass, and so really nothing would change for a uniform gravitational field. So these are automatically ruled out. So now how about measurements of the behavior of the object as it floats in water? Well, one thing is that, again, water will not be able to go inside the sphere if we have, a solid sphere versus a hollow sphere. Immersed in water. They would still have the same mass and the same radius. And so ultimately, they still displace the same amount of fluid. In one case, the entire sphere is displacing, or the entire sort of solid sphere is displacing fluid, but in the other case, it's just the ring of, or the sort of hollow sphere of mass, but then the air or the vacuum inside also displaces water. So they still displace the same amount of fluid. And so they still have the same buoyant force, and they would still exhibit exactly the same motion. And in fact, the fact that the buoyant force is dependent on gravity, right? Because the buoyant force is the result of the pressure differences in water at different depths, and that only occurs due to gravity. And gravity really cannot tell the difference between these two spheres, and so it intuitively makes sense that the buoyant force can't tell the difference either. And again, all the properties that could actually influence the buoyant force or the behavior in water are again the exact same from the outside. The mass and the radius and the shape of the sphere are once again exactly the same. And so now D is ruled out too, and so really B has to be the correct answer. But let's verify that we actually can tell the difference. So option B says measurements of the time it takes the object to roll down an inclined plane. So why does this make a difference? What makes this correct? So, now that we've ruled out everything else, we could proclaim victory, but I would at least like to discuss the reason that this happens. Basically, these two have different moments of inertia. And this is this is really the critical difference between a solid sphere and a hollow sphere. And in fact, if you had seen the options and just seen option B, you might have just immediately know that that's the correct answer and then just move on. So a solid sphere, solid uniform sphere, has moment of inertia equal to 2/5 mr squared, while a hollow sphere has moment of inertia 2/3 mr squared. Intuitively, it makes sense that this should be greater because more of the mass is concentrated on the edge, whereas here, away from any axis of rotation. So again, this is for an axis of rotation that passes through the center. It makes sense because here all the mass is really, or much more of the mass is concentrated away from the axis of rotation, whereas here you have all this interior mass that will be closer to the axis of rotation. And I'm not going to attempt to derive these. That should really be in a video of its own. But these are two quantities. These are two of a few moment of inertia that are worth committing to memory. But from these two moment of inertia, you can then conclude that this one will roll slower down a ramp. And why is that? Well, basically, the rotational, when an object rolls, it has total kinetic energy equal to translational kinetic energy plus the rotational kinetic energy. So the translational kinetic energy will basically just be as if the object were shifting and really just from the motion of the center of mass, and the rotational kinetic energy comes from the motion of the object around the center of mass. So really the motion in the center of mass frame, in which it would look as though it's just rotating without moving. And basically, as the moment of inertia increases, the rotational energy forms a greater and greater fraction of the total kinetic energy for rolling without slipping. And so as these two objects were to roll down a ramp, well then, if you look at its speed at any given point, then both of them have acquired the same kinetic energy due to the change in height, which results in a change in kinetic energy. But for the hollow sphere, k rotational will be greater, will take up a greater fraction of the total kinetic energy, so k translational will be less, meaning that its center of mass will have to move at a slower speed, and thus it will go down the ramp slower. You can also derive this by balancing forces, so you can draw out the force diagram and see that the force of static friction is what will contribute to the rotation, and from there you would end up also reaching the same conclusion that the acceleration for the object of greater moment of inertia would be less. And so either of those ways will work to show you that this will indeed tell you the difference. And so thus B is the correct answer. All right, that concludes this problem, and I hope that was helpful. Thank you for watching.